Hello, everybody. I'm Dr. Leonardo Barilaro, and thank you for the introduction. Today, I will present the results of a study that has been focusing on 3D printed shields. And the results that me and my colleagues found are very interesting. This is a paper done in collaboration with the University of Padova, and I'm a senior lecturer in aerospace engineering for the Malta College of Arts, Science and Technologies, MCAST, focusing my research in the field of space debris, or better, the effects of the space debris following hypervelocity impacts. And I'm also a pianist, merging very often projects with the scientific part and the artistic part. And this afternoon we'll have another presentation about the artistic part. So, the project of today regarded the idea of having a relatively cheap and fast way for rapid prototyping spacecraft shields in composite material. And everyone nowadays talks about additive manufacturing, a little bit less than AI, but is still a buzzword. But how good it is? Where can we really apply it? So, with the SBORAEK project developed in Malta, we designed these shields, and we wanted to see the ballistic performances of these shields. So, the primary goal, as I was mentioning, regarding the enhancement of the shielding capabilities in comparison with traditional solutions. And here you can see some shields samples. We 3D printed different geometries with different parameters, having one main concept all throughout the design campaign. So the outer shell made of CFRP for tackling the structural stiffness, and the inner core made in Kevlar to use it for its absorption properties. Now, a first hypervelocity impact campaign was performed to evaluate the performances. We used 3 mm aluminum spheres, impact velocities compatible with the LEO range, and with tests between 3 and 5 kilometers per second. And we tested both single plate and multi-plate shields. Now, the core of what I'm presenting today is comparing the ballistic performances with traditional CFRP shields with the new one, and seeing how good or how bad they were. And the results we found were pretty interesting, and as I will show you soon. So, here you see an image that shows one of our benchmark tests done with a traditional CFRP panel, where on the back you can see the copper witness plate that collects the ejected debris to be analyzed post-test. And here you see an example of a test done with a two-stage light gas gun, in this case at TO Engineering in France, where we tested one, more than one, but here is one example of our 3D printed shields. Now, after the test campaign started the less fancy part, the part that can be also very tedious at a certain point. Why? Because basically in literature there is a modeling gap. What does it mean? It means that standard models applies to traditionally manufactured shields. And it's hard to predict the behavior of a 3D printed material. Why? Because you have an anisotropic behavior. There is the concept in this case of layer by layer deposition, and above all with relatively cheap 3D printing solutions, so you have a presence of process-induced micro defects that increase the uncertainty range once you start creating shields with the same nominal properties. So we had the need to have a new validated simulation model to be applied to these shields and be optimized for that. So, as Alberto introduced earlier, in Padova, they use a proprietary developed software called Collision Simulation Tool Solver, CSTS, that is able to simulate impacts on complex structures, including composites. And the model basically creates macro elements and uses a dedicated breakup algorithms to analyze the evolution of the damage, and this is based on so-called Voronoi algorithms. And the cool part is that the solver can be tuned and optimized using empirical data. So, once we had the first results, there have been the answer using the CSTS software as it is, and a significant mismatch with experimental data was found. Why? Because the model for the traditional CFRP was overestimating the damage, so was predicting larger craters and bigger delamination areas of what we had as experimental evidence, and was also overestimating the mass loss. So that standard model was not adequate for the purpose of our research. And here you can see an image on the wave, also the images previously showed, where the software follows each fragment and analyzes the velocity and the trajectory. And this, as can be comprehensible, works very good above all for the bigger fragments. Now, how do you adapt a software that is overestimating damage? So, first of all, the biggest parameter leading to the largest errors were identified, which was crater diameter and frontal delamination. And new correction equations were introduced through regression techniques and selected candidate equations with corrective factors to scale the parameters based on the impacts velocities, the parameters of the test, and these equations were applied to our tests. Now, the results were pretty satisfying for being, above all, a preliminary study. Why? Because the adapted model showed much better performances. And here in the image, you can see in green the model, the software before having the adaptation. And you can see in red the real data. And as you can see, between red and green, there is quite a over-assessment of crater delamination and mass loss. With the model adapted, so the dots in blue, you can see that this uncertainty range became much more reasonable. Above all, talking of the crater diameter and the frontal delamination area. So this was really encouraging. Here you can see one example of a test with the front and the back of the impacted sample, where besides the crater you can see also the delamination of the layers. And in these graphs you can see a comparison where on the top you see how originally the software was assessing the damage, and on the bottom there is the corrected model with a much smaller area that are much closer to what you saw in the images of the real test. Now, the results were compared with what was measured. All of the samples were passed through a scanner and the main dimensions and parameters analyzed. So we got that the new model produces fewer fragments, which is closer to the reality, and this is reflected in smaller damage areas. And also the overall distribution of fragment velocities and angles is pretty close to the observed ones. Now, of course, it's not everything with golden flowers. There are still a lot of things to tweak and improve. And we found some limitations in predicting the smaller and hence fastest fragments. And this is also due to the simulation resolution threshold that is implemented in the software. Now, as very encouraging experimental findings, we can say that yes, additive manufacturing is a buzzword, and in our case is really a game changer, so thumbs up. And in this way, above all in this growing space economy, we have a reliable, rapid, and relatively cheap way for prototyping spacecraft shields. And also what really made us very happy is that these 3D printed shields showed better ballistic performances in comparison with a traditional one. So also this is a win. So what we got? We got that the 3D printed shields for the SBORAEK project produced smaller frontal craters, so indicating also better resistance. And also we did at a very early stage, because we didn't have for now so many tests available, we did different types of printing, and shields printed horizontally, which for us, if you check the paper, means shields printed with the bigger face parallel to the 3D printing plate, showed better performances in comparison with one printed vertically, so printed in a normal direction. Now, simulation is key because, of course, to do tests is time-consuming and also expensive. And the results with CSTS were really encouraging. And having a validating model, for sure, is a powerful tool that can fast-track many design activities, above all at a conceptual stage for any given space project. Now, we are already working on the next steps. So in the pipeline, in our workflow, there will be a much larger hypervelocity impact test campaign with much more tests. And we already 3D printed the new generation of shields based on the lessons learned. And in parallel, there will be the refinement of a model to improve the prediction that the solver is doing. So, thank you very much for your attention, and I'm very happy if you have questions to ask. Thank you.